Nobody told me.
I didn't know either, by the way.
As I said,
I'm serious.
Nobody told me.
Hi, welcome everybody, and thank you for coming. It's a pleasure to have among us today Professor Sheila Hemami from Cornell University. Sheila did her undergraduate at University of Michigan and finished her graduate degrees at Stanford University. She was with Hewlett-Packard for a year before joining the electrical engineering department at Cornell University, where she's currently a professor. She obtained an early career award from NSF and several national teaching awards. She also had the Kodak professorship at Cornell from 96 to 99. She was a Fulbright Distinguished Lecturer in 2001. She's a senior member of the IEEE and is currently chair of the MDSP committee, and has served as associate editor of several journals, including Signal Processing. And she's also the programming director for the Cornell Advanced Center at Cornell University. And she'll be talking about some of her work today on signal processing approach to vision. And it's a pleasure to have you. Thank you for coming.
Thank you, Hamid. So when I get that type of information, I always think that I should change my bio to say Sheila will give today's talk. So the title of today's talk is A Signal Processing Approach to Modeling Vision and Applications. And technical person, can you hear me? Is it possible to make this bigger?
No. Unfortunately not.
Okay. Okay, so, well, we'll see how things go. So papers on everything I'm going to talk about, and then some you can find at our group webpage. So let me try and give you a little bit of motivation as to the types of problems that I'm interested in and how I got interested in these problems. So if we look at what I'll call current state-of-the-art techniques for image and video compression or representation, we have a very, very big cog, which I've labeled here as signal processing machinery. Okay? And what I mean by that is we now have very, very sophisticated signal processing based techniques for modeling images and video, and for essentially putting them into a big bin of heavy-duty mathematics and churning quite well. Okay, we have excellent statistical models for these signals, at least from a completely signal-based standpoint. We have a lot of good, very effective frequency-based techniques for dealing with them. We know how to quantize them. We have very sophisticated entropy models. So, and we put a very, very little bit of human visual system modeling into the big box that has the machinery. Okay? So I think everybody's familiar with JPEG at this point, right? JPEG 2000 has a lot of improvements on the signal processing machinery. MPEG 4, H.264, advanced video coding, pretty much any video or image compression technique fits this mold. And this mold works pretty well when resources are not limited. Now really what I want to say here is this model works well when we're coding at high rate. In other words, when you look at the video that comes over your satellite TV or through your digital cable, or you look at the images that came off of your digital camera, they look to you effectively undistorted, right? They look as good as the original. They do not look bad. There's enough bandwidth available to represent that information in a visually lossless manner. When we don't have enough rate to represent these images in a visually lossless manner, all of the underlying models around which the signal processing machinery was built are no longer valid. And therefore, these techniques break down. And the manifestation of that is that when you look at images or video at very low rates, compressed with what we have, JPEG, JPEG 2000, H.264, MPEG, it looks terrible. Okay, it looks beyond terrible. It's generally unusable. Okay, so the motivation was, well, if we don't have a lot of rate, what is the best way that we can possibly represent these images in a manner that they're still going to be visually useful? Okay. Now, one approach to this would be to just develop different signal processing machinery for low rate data. Okay, but I'm lazy, and I thought, you know, we as a signal processing community have done very, very little work on really trying to understand how we comprehend this information. And I suspected that there was a lot of gain to be had there. If instead of trying to develop much more sophisticated mathematical techniques, let's actually try and understand first, are we really coding the information that is visually important? Or are we just coding information that somehow our statistical model, which we liked because we could express it in terms of Gaussians or things that have names that we know, said it was important? Okay. So our goal in all of this is first off to develop more accurate models for the human visual system, such that when we take those models, and this is the big difference between what I do and what psychologists or neurophysiologists do, I don't just want a model that says, this is how the visual system works and it's yet another of umpteen visual models. I need a model such that if I put it back into an image or video processing system, that system then gives me better performance, where better can either be for the same rate the output looks better, and looks better means you do a proper experiment, set 20 people down in front of it, at least 15 out of 20 say yes, it looks better, or for the same visual quality, I get a substantial savings in rate. Okay. And then once we understand how we see as it pertains to what we want to do, which is represent information, what new or better or improved signal processing machinery is really going to exploit that understanding. Okay, so hopefully that's what I'm going to talk about a little bit today. Okay, now just to check, my target time for completion is 10 of, is that correct? Yeah. Okay. Okay, so now this is one of these slides that I think that to everybody in the room, okay, can you see the difference between these two images?
The right is better.
Okay, well you think the right is better. So I can take an image and distort it in any manner of ways. I can add Gaussian noise. In this case, we have compressed this image such that it shows visual artifacts. We've used both JPEG, and hopefully everybody can see the blocking artifacts on the left-hand side, which we're used to seeing from JPEG. And on the right-hand side, we've compressed it using JPEG 2000. Now, because of the content of this image, you may or may not be able to see the compression artifacts in that right-hand image. So if we had a larger screen and better quality, what you would be able to see was that there's a lot of blobs in the child's face. Now, I think we can argue blobs in a face look more realistic than 8x8 blocks. Okay, but nevertheless, there are some artifacts there. And in fact, that image has been compressed not only using JPEG 2000, but using an optimized set of quantization step sizes based on some of our work. Now, statistically, if I show this image to 100 people, about 75% of them are going to say the image on the right looks better. And for the most part, I can take any image, mess it up in many ways, show them all to you, and you will always be able to say, I think this one looks the best. Okay, even though they all have different types of errors, we just intuitively tend to prefer some types over another. Okay? It's easy for us to make that judgment, but how can we, in a rigorous manner, identify and then create the better image? Okay, my goal is, given some amount of distortion that I need to add to an image, I want to create the image that is going to be the better image for the largest percentage of people. Okay. So roughly what I'm going to talk about is first off some classical psychophysical results. Okay, if you go and take a class on perception, okay, what are you going to learn about how we see? How is the visual system typically characterized? I'll then mention very briefly wavelets, which hopefully everybody here has heard of, the multi-channel model, which is a filter bank model for the visual cortex, V1, and images, how all these fit together. And then I'll talk about some of the experiments we've done to characterize natural images. Now, that all may be somewhat abbreviated. And what I'll finish with is some signal processing strategies then which actually exploit the characterization. So we'll look at some results in the end to see, did we achieve the goal? Can we do this? Okay. So the first step in all of this is to understand the human visual system. Now, this is a model for the human visual system that you can find again in any textbook on perception. And what I am interested in particular, I'm not going to go through the whole thing, is this point, this block V1. Okay, so V1 is the cortex. It sits at the base of the skull. That's why sometimes when people get hit in the back of the head, they can't see very well. And all this business beyond V1 starts to appeal to cognition. Okay, and we are doing some experiments now and some work that actually deals with the V2 area and some cognitive information. But what I'm going to talk about today is V1. And the reason we like V1 and find it appealing is that it can be modeled as a filter bank. Okay. Now, 3 classical results that essentially pertain to V1. Now, all of these results are obtained using sinusoidal gratings, and a sinusoidal grating is exactly what we see on the screen. So this is a sinusoidal grating in one dimension. If we slice it horizontally, you get a sinusoid. If we slice it vertically, you get a constant. And I've also modulated it with the Gaussian, so it fades out a little bit on the edges. So people are shown these sinusoidal functions, and the first classical result is the human contrast sensitivity function, or the CSF. Now, the way that the CSF is derived, and there's a lot of text here, let me just talk about it. People are plunked down in front of a CRT. Okay? CRT is blank, so just a gray screen, and they're given a knob. You turn the knob, and you turn the knob, and you turn the knob, and at some point you realize your screen is no longer gray. You actually see a little bit of variation in the middle of the screen. The point at which you say, aha, I now see something, instead of understanding that there's just a flat screen, is your contrast threshold. And you can just think of that really as an amplitude measure. How big did the sinusoid have to be before you could actually say, okay, I see something there? Now imagine we repeat this experiment with you many times. We change the frequency. Okay, so instead of just that one sinusoid, you have sinusoids that vary more, sinusoids that vary less, and with many other people. And what we end up with is the CSF. So the horizontal axis here is spatial frequency. Okay, what is spatial frequency? We measure it in cycles per degree. So first let's talk about degrees. We assume that we have 180 degrees of visual field. Okay, now obviously if I wiggle my fingers out here, I don't quite see them as well as if they're in front, but 180 degrees. And the numerator, cycles, is essentially in that 180 degrees, or in some subset of it, wherever the target is, how many cycles of the sinusoid were there. Okay? The y-axis is sensitivity. So a higher sensitivity means it was easier for you to see. So 2 things to note. One is this is a log-log plot. Okay? So we have a peak somewhere between 1 and 10 cycles per degree. You'll see that quoted a little bit differently. But then we have a very, very, very steep fall off, okay, on a log-log plot. So effectively, with respect to seeing sinusoids, we are low-pass filters. Okay, now we do also have a little bit of a fall off when we come to lower frequencies. If you think about this, as your frequency gets lower and lower and lower, you start to really be unable to tell, you know, when you get to very, very small numbers of cycles, is there a gradient or not? Okay, so this fall off is not really so interesting. It's the high frequency fall off that we often cite. Okay. Now, what did I not tell you about the CSF? For one, I didn't say anything about orientation. Right? I didn't say, oh, I showed you horizontal or vertical sinusoids. It's just cycles per degree. Secondly, it's just for sinusoids. Right? How often do you walk down the street and say, oh, look, a sinusoid? I can see it. Okay. And lastly, we say that it represents sub-threshold perception. So remember I said that you turn the knob just until you barely saw it. Okay? Let's extrapolate a little bit. When you get, say, a picture off the web and it's been overly compressed using JPEG, those blocks are in your face. Right? It's very obvious to you that that image has distortions. So those are not just at the level of perception. Okay? They're very, very obvious to see. Okay, nevertheless, we happily apply the CSF to many image processing functions. Okay. Now the second result is contrast constancy. I'm not going to try and explain this, but what I'm going to just point at and sort of ask you to believe me, notice up at the top of the plot here we have something that kind of looks like the CSF, something that rolls off. But then these graphs tend to get flatter and flatter and flatter. Okay? And what this plot is demonstrating is that as it becomes very easy for you to see that there's a sinusoid on the screen, you lose your low-pass characteristic and you become all-pass. So if it is easy for you to see something, it is as easy for you to see a high-frequency pattern as it is a low-frequency pattern, okay, over a large range of frequencies. So we lose that low-pass characteristic. Okay. Now the second feature or classical result is summation. So the summation question is the following. Notice I've changed my little sinusoid there. If one stimulus, one sinusoid, has some particular contrast at which you just saw it on the screen, and a different stimulus had a different contrast. And in this case, I was lazy. I just rotated my sinusoid. But you can imagine that this second stimulus could be a different frequency in the horizontal, in the vertical direction, or it could even be at a 45-degree angle or something. If I know when we see these two things, can we predict when you would be able to see this grading? Okay, so you turn the knob and turn the knob, and all of a sudden you see a checkerboard pattern. Okay. Now, the answer to this, I'm not going to explain. I'm just going to point to one variable in this equation. Okay, so there's some psychophysical theory that this following equation comes from, and the variable of interest is that beta term. Okay? For sinusoidal components, that beta term is somewhere between 2 and 4. Okay? And essentially it says, well, this isn't a linear combination. If you know two thresholds, the thresholds don't sum linearly. They sum in a more sophisticated way, with that exponent beta being between 2 and 4. Okay, I'll come back to that 2 and 4 later. Okay. Now, just to say, what does that 2 and 4 mean? What it means is we're 40% more sensitive to something if we show it along with something else. Okay, it is easier for you to see two things at a time than just one. Okay. Now, the last result is masking. I'm not going to explain that here because I'm going to talk about some experiments that we did later. But the idea behind masking is items 1 and 2 deal with sinusoids. Okay, now I'm going to intuitively explain masking. Masking is the concept that if you look down at the carpet in here, it's quite detailed. So if we put some white noise on top of the carpet, we would say that the carpet texture hides the white noise, right? You wouldn't be able to see the white noise until there was a lot more of it, as opposed to showing you white noise on a flat background. Okay, so the idea of masking is other image content can hide whatever it is your particular target is. Now, standard masking experiments are also done with sinusoids and white noise, but the idea is that the image content influences how easy it is for you to see some particular component. Okay. So the signal processor's question is, can I take these 3 classical results and apply them to processing images? Okay, now, one answer is yes. We've been trying to do that for many years, and you can argue that certainly JPEG and JPEG 2000 to some extent do a little bit of some of this. Okay, but what do we know? Okay, all of those results came from sinusoids. Fourier tells us that images are the superposition of many, many sinusoids, not just one and not just two. Okay. Secondly, images provide very sophisticated masks to what's actually going on, and they have higher level meaning to observers. Okay, if I showed you a very blocky image of your grandmother, this starts your brain going, oh, grandma, her apple pies, and you then become less interested in the pixel-based content because your brain is off running after other things. So the signal processor's answer to this question is no. Okay. So what I wanted to do is ask the following question. Instead of sinusoids, I want to use realistic maskers, images, right? Because whenever you see distortions in an image, we can say that the errors are effectively being shown on top of an actual image. So let's use an image as a masker. And instead of showing people sinusoids or white noise, let's show them realistic stimuli, which is actually the spatially correlated bandpass noise that we get from quantizing some components of an image. Okay? So we want a CSF both with and without masking, but for images with a target being band-limited correlated noise. We'd like to know if I show people multiple errors in an image, how easy is it for them to see all of them? So this is the summation question. It goes back to that beta. Is it 40% easier to see them? What is the beta number when I show people images? And if I take any image, can I predict exactly how much error I can inject into that image before the average person is going to see it? Okay, so this is the masking problem. Okay, now I'll just give you a little bit of an idea. Now we're going to talk about wavelets. So I mentioned that V1 we like to model in the vision world as a bank of filters. And our tool for the images here is going to be the 2D wavelet transform. Now, intuitively, what does this give us? We start off with an input image, and we put it through one low-pass filter and 3 high-pass filters. So the low pass, and after each set of filters, we're going to downsample horizontally and vertically. Now, intuitively, if I take an image, low-pass filter it horizontally and vertically, and downsample it, what do I get? A smaller, blurrier version of the original image, right? And that's what we see just coming off the low-pass filter. Now, the high-pass filters are going to be high-pass directionally. So if I low-pass filter in the horizontal direction and downsample, I just have a blurry, skinny version of the image. But then when I take that and high-pass filter it vertically, I end up passing the horizontal edges. And that's what we see in the first output. We get very strong horizontal edges and not much else. Change the direction that the filters are operating, so now I'm high-pass filtering horizontally, we see the vertical edges. Okay. And lastly, we're going to high-pass filter in both directions. And this process can be repeated on the low-pass image. So as a result, we end up with edge information at various scales of the image. So this is our tool for analysis. And if we look at the wavelet decomposition in frequency space, okay, my plot here has, I'm going with normalized frequency here. So pi is equal to half the sampling rate. Horizontal frequency on the x-axis, vertical frequency on the y-axis. This is, of course, assuming ideal filters. So what we see is we have square frequency bands that also get smaller by a factor of 2 in each dimension as we move down toward DC. Okay. Now keep this picture in mind, and then let's look at a model for what the visual cortex is doing. Now keep in mind, this is the quadrant 1, right, the upper right quadrant of two-dimensional frequency space. So you want to compare this picture with the upper right quadrant here. Okay, so again, I've got horizontal frequency and vertical frequency on the 2 axes. Now, instead of being normalized to radians, I've got this labeled in terms of cycles per degree, because this is actually the cutoffs for the filter banks in our cortex. So what we see in common with the previous slide is as we get out from the origin, the pass bands of the filters are bigger, right? What we don't see in common, there are no squares here, right? You will never get these pie-shaped wedges from separable filtering operation. Okay? Nevertheless, we as signal processors still like to say, gee, this is close enough to this. Okay? There's the laziness factor. So just remember this. The next time somebody says, we use wavelets because it's well matched to the brain. No, it's really not. Okay, so give them a good heckle. Okay, so just what are we actually looking at? So there's one more key point I want to make here, and then I'll try and give you some results. Pixel values are the p terms here. That's what we actually manipulate in C and MATLAB. That's what's stored in our computer. So if we're talking about grayscale images, p runs from 0 to 255. If you have color images represented at RGB, p runs from 0 to 255 for R, for G, and for B. Okay? You don't see p. What you see is an output luminance on a screen. That luminance is some photons that are coming out from the screen. We measure it in candelas per square meter. And it is related to the 0 to 255 value by this nonlinear function for CRTs. Okay? And because I care about what people see, I have to make sure that I'm doing all of my measurements using the displayed luminance. Okay? And generally, this is important if you really want to take into account what people are seeing. Now, of course, the difference here, the challenge, is that the other parameters here, B, K, and gamma, these are all functions of the display. So what this means is that people looking at the image on different displays are going to see different images. Now, you know this. If you and your friend both go to the same website on both your laptops, and you actually look at what you're both seeing, you're going to see different things, right, depending on how you have your colors adjusted and everything else. Now, we measure or we quantify everything we're going to show people in terms of contrast. Now, in English, contrast is very easy to define. It's luminance change over background luminance. Now, I say in English it's easy because there are many, many different equations for contrast, and people use a different equation depending on what their application is. So we will use RMS contrast. And all I want to say about RMS contrast is exactly what you would think. So instead of P's, we're using L's. We take the root mean square value of the luminance, and then simply normalize it by the mean luminance. And by using a Taylor series approximation, as long as we know the parameters, we can actually compute this as a function of the standard deviation of the pixel values, right? So thinking a little bit about computation here. Okay, so what types of experiments are we doing here? Let's skip this. So remember I said I want a masked and an unmasked CSF. Okay. So one of the things I'm going to show people is simply the image on the far right. Now, in order to obtain this image, what I've done is I've taken an original image of a blue jay. I've done that wavelet decomposition like I did with the dog. I take one of those high-frequency subbands, just one of them, and I quantize it. Okay. I then subtract the two, and I end up with the quantization noise. Now, obviously, these two images have the same mean, so I've added 128 to this so it doesn't look black. Okay. Somebody sits in front of a CRT, and again, intuitively think they have a knob. They turn the knob, they turn the knob, they turn the knob. But instead of a sinusoidal grating appearing at some point, what they get is this. So the first thing I want to know is, at what point were people aware of the fact that they were no longer looking at a gray screen, they were seeing something like this? Think of it as a pattern of blobs. Okay? The second question that we asked people was we showed them both of these images, the original and the quantized. Again, think that you have a knob. You turn the knob, you turn the knob, you turn the knob. At some point, you can tell there's a difference between the two. Right? You start off, the two images look the same. You increase the quantization until at some point you say, aha, I can see the difference between these two images. And if you're having a hard time seeing the difference, look at the ringing around the head. Okay, we see extreme ringing there. And this is a nice example of masking too. We can see the errors around the head. We really cannot see the errors in the body, even though when we look at the noise, there are errors in the body. Okay, so that's some masking at work. Now we do the same thing with summation. So this is the same summation question I asked before with the sinusoids, but now I'm going to show somebody this. Turn the knob, turn the knob, turn the knob. At some point they recognize that. Now this means nothing to you right now, but we measure threshold for that. And then we do the same thing in a masked manner, and this is exactly the image that came from. So people are given this image and the original and asked, when can you tell that there are distortions there? Okay. Okay, so what do we get? The CSF that we saw before is this dashed line. The unmasked CSF for just the blobs is the line we have up here. And when we put the image on top of it, we lose sensitivity by an order of magnitude. This is not particularly surprising, right? We saw it with the bird. It was much harder to see the errors in the middle. But we start to get an idea of what the CSF is when we show people these things. Now, just so you know, this is about 80 observers and 15 different images. Okay, so it's not just the bird image, it's not just one person. This is a sort of a statistical snapshot of how we see with respect to quantization, noise, and images. Okay. Now, from the summation standpoint, again, remember I kept saying beta is between 2 and 4. When I showed people two subbands quantized at the same time, we got this beta number, which I sort of waved my hands and didn't really tell you what it was, between 1.5 and 1.8. Okay, now woohoo, I'm an engineer. Let's approximate it as 1. Okay? Now when we approximate it as 1, we get linear summation. Okay? This means if you see something at one threshold, you see something else at a different threshold, you add them together, they're going to become 50% easier for you to see. Okay? Linear is much easier to deal with mathematically. That was one of our engineering motivations for clipping this. Now, what we found, though, when we made our engineering decision, is that linear summation had been observed before. And linear summation was observed in experiments that had to do with object recognition. Okay? I did not ask anybody to recognize anything. I said, when do you see the difference between these images? Or when can you tell that there is something on the screen? What does this suggest? This suggests that you cannot divorce your brain from thinking about what it's looking at, even when you're only asking people to make an aesthetic judgment. Okay? And that brought us to the concept of global precedence. Now, global precedence is a psychophysical, I don't know if I should call it a theory, or I never have the right words for these things. But the idea of global precedence is the following. when we look at the world around us, our visual systems integrate what comes in through our eyes from coarse to fine. So essentially, we take the outputs of those bandpass filters in our visual cortex, and the first thing the brain does is it processes the lowest frequency. And then it adds the next on top of it, and on top of it, and on top of it, and on top of it. So we integrate from low to high frequency. Now, what global precedence tells us, so what I've done here is just taken a picture of a duck, and for illustrative purposes, I've broken it down into low frequency, mid frequency, and high frequency. So your brain would just integrate. It would start here, add this, add the top thing, and get the picture of the duck. Now, what global precedence tells us is if we break the integration chain, you can't pick up where you left off. Okay? So you start to integrate, and all of a sudden there's frequency information missing. You can no longer integrate what comes out of after that into the structure. Instead, you perceive it as noise. Okay? And I used to have a demo slide that actually showed this, but I found that on everybody's projection systems, everything looked the same. So I leave that out now. So you'll have to trust me that if I show you the duck with the first two scales, you see a blurry duck. If I show you the duck with just this thing added in, you see a noisy duck. So even though this is perfectly valid information, your brain can't use it, and it actually makes the image look worse. Okay? The implication for compression is as soon as we've pitched something, we need to look at the whole frequency decomposition, make sure we don't add anything in, which is just going to be perceived as noise. Now, this sounds obvious now, okay? But this was something that we as a community didn't understand. Because from a mean squared error standpoint, this information is just as valid as this information, right? Unfortunately, the brain, we don't see in mean squared error. Okay, I think what I'm going to do is I'm going to skip all of our masking stuff and just show you some images. So all I want to say from the masking perspective is that we generated a better masking model that takes into account content as you cognitively think about. Okay, so I want to end up with 3 examples that actually take some of these visual system results and put them into some algorithms. So hopefully, if you didn't believe anything else I said, the numbers hopefully will speak for themselves. So I'll give 3 examples, and I'll probably focus on the first 2. The first is what we call distortion contrast quantization. What I would like is compression that is going to be visually optimal at all rates. Okay, now I'm playing fast and loose with the word optimal. What I mean here is that if you give me a rate, I can produce an image that a majority of observers will prefer to any other image produced at that rate. Okay? And then I'll talk about some spatially localized quantization that uses the stuff that I just skipped. Okay, so first thing that we wanted to do was say, well, let's come up with a quantization strategy for wavelet-coded images based on the set of results that I've spent my time talking about. Okay? So the end result here, really, that if you leave this room, 30% lower rates. Okay? Now let me put this in context. In my world, if we get a file size that is smaller by 2 or 3% using the signal processing machinery, this is huge. Okay? 2 or 3% is huge. So to come up with a visual system model that when plugged into JPEG 2000 makes the images 30% smaller, just goes to show how much slop we have, okay, in current representation systems. So, boy, these are all going to look the same. Well, let's look at the high definition screen, see if you can see something. Here's our original image. Okay, and if we go into JPEG 2000 and use either the default quantization or a different quantization strategy, and let me just say, the only difference between these 2 images in JPEG 2000 is there are 15 numbers which are different, 15 different quantization step sizes. What do we get? Okay, so what I want to point to is, first off, look at the water. I would argue that on the right, the water looks more like water and less like heavily quantized water. Okay? Secondly, look at the skyline. Okay, it's extremely foggy or smoggy on the left, and on the right you can actually see quite a bit of detail in the skyline. Okay, so that's been preserved. The boat also has a lot more details, and lastly, take a look at the diagonals on the boom for the crane. There's a lot of ringing in the left-hand image. In the right-hand, so what I mean by diagonals on the boom is look at these two strong diagonals here and over on the right. Okay. Now what's remarkable about this, there is nothing spatially localized in this. Okay. In no way in these images did we zoom in on any one place and say, oh, let me concentrate on this. This is simply done with coming up with 15 different numbers. Okay. So it shows there's a lot of gain there. Now if you're a mean squared error junkie, let me just point out, this image is much better in mean squared error. Okay, in spite of the lousy looking water, the loss of the background, the ringing. Okay, so we really, I always cite mean squared error myself because you have to. Okay, but you never want to actually make any quality judgments on mean squared error. Okay, so what do we get for a bit rate savings? Now I already said 30%. If we take these two images, for the cat, we don't see a big difference. So the teal is using the new 15 numbers. The pink is using the default 15 numbers. The best we get is about 18% smaller in maybe mid to low visual quality and a slight loss at very high quality. Now the cat image has a lot of detail. I don't think you can see that on this picture, but he's got a lot of fur. The whiskers are very, very fine, and the fact of the matter is you have to keep those around. Okay? But when we go to the Rain River, this is where we start to see gains in the 30% range. Okay, now we've since tweaked this where the gains are closer between 20 and 30 sort of across the board. So if we take into account how we see, we can do a lot better. Okay, now the last application I want to talk about is overhead-free optimal spatially localized quantization. So the material that I skipped that had to do with sort of tuning the masking to what was going on in the image does suggest a spatially localized approach. If I can tune how much error I should put into different regions depending on what they are, then I should be able to do better. Okay. Now the big problem with any type of labeled compression where you're going to tune to different regions is that you have to send the region map. Right? You have to convey not only what you did but exactly where you did it. And up until now, this is where these techniques have always lost out. They did well when you optimized something for each area, but as soon as you add in the extra information, you've now bloated the file back up past where you were to start with. So our solution was simply to say, gee, conditioning reduces entropy. Maybe I can use the map for the regions to actually do a better job of compressing. So in fact, that's exactly what we did. I'll not go through this. Just remember, conditioning reduces entropy. So what do we end up with? So I've got 4 images here. We just looked at 2 different rates here, horse and the rhino. The first set of numbers tells you who liked which image better. Okay, so if we just do a baseline comparison with a good compression technique, we're beating it either 8-0 or worst case 6-2, 75%. Okay, and just from a psychophysics standpoint, 75% is really the best you can ever hope for. Okay, so these ones were really blowing it away. The other thing I want to point out, again, for the MSE junkies, if we look at the case where 7 people preferred the proposed technique to 1 preferring JPEG 2000, the PSNR difference is almost 5 dB. Okay, this is enormous in terms of a mean squared error difference. So we're being even sloppier mathematically in representing the image, but we're being much more accurate representing it visually. Okay. So this is one example image at threshold. This is supposed to have errors in it that you barely cannot see, and I'm sure that given the viewing distance everybody has, I'm positive you can't see anything. Okay. And this is a map of where the errors ended up. So if you compare this with the original, you can see that this technique is doing a very good job of really strategically pushing those errors into places where you can't see them. And again, this image in terms of mean squared error is just enormously flawed compared with something that would come out of JPEG 2000. Okay. So let me skip the multiple description. Just mention there's one more thing. So hopefully what you'll take away from this is the idea that if you want to get a lot more bang for your buck with respect to representation and compression, if we put a little bit more energy into understanding how we see and how the human functions as a receiver, we can actually get very, very large gains. Okay? Now we still need traditional signal processing, good math, in order to fully exploit there. Okay. And I'll just mention that I've also applied here as still images, which I can assure you is very painful from an experimentation standpoint. Okay. So I'll just end up by acknowledging pictures that you are.
Let's NC UNC. I'm not sure. All right. If not, are there any questions here?
Okay. If you're shy, you can feel free to ask me questions afterwards. Well, I never want people to feel like they have to stay in their seats until the one person asks the sacrificial question, and then you can all leave. You know.
Yes, Glenn.
I don't know if I missed the theory behind it, but how are you cramming all of these errors into a location in the image where it does the least harm?
Yeah, so I didn't talk about that. So we did two things. The first was we did some experiments to quantify based on labeling a region in an image as a texture, which is basically some type of stochastic pattern, an edge, okay, which is something that you don't recognize, but you definitely see a strong edge, or what we call a structure, which is something that has higher level meaning to you. So you would see a little patch, maybe if it had my eye in it, you would immediately recognize that as eye. Okay. We quantified, based on essentially the cognitive importance of the region, how much error could each type of region tolerate. And then I actually had an undergrad come up with an automated segmentation technique based on blocks. So what we're doing is taking the image, segmenting it into blocks, labeling each block as an edge, a texture, or a structure, and then using that label to determine, that label in conjunction with our previous results, to determine how much error and into what frequencies we're going to inject the error. So no, you didn't miss it.
A lot of what you presented is done in terms of JPEG and these block methods where they're working with 8x8 blocks or something else there. What's the future of going with structures that are not block oriented, doing segmentations that are based upon the objects in the image themselves and keeping things away from having to deal with rectangular blocks?
Okay, so the question is, can we go to something that's a little bit more truly visually and cognitively related?
Yeah, visually.
So the theoretical answer to that is, I think it's well known that if we could go to a purely object-based representation, then we could easily get 2 orders of magnitude more in terms of compression. The downside of that is the computer vision people have been trying to solve this problem for decades and really haven't gotten anywhere, which makes me think I'm certainly not going to be able to do anything either. I personally don't have a whole lot of hope for that any of our current approaches are the right way to do that. So without question, it is a more efficient representation if we could figure out what to do. But
you still have your mask in that case, and the mask is going to take a bunch of bits.
yes, exactly. And to some extent, we saved ourselves on the spatially tuned stuff by making this realization that that conditioning reduces entropy. Now, of course, we have a big piece of a priori information, which is that we knew that we had segmented into blocks, and we knew how big the blocks were. So I'm a cynic on these things. Yes, it's the right thing to do. No, I don't have a lot of hope given anybody's current approach.
You said you applied this to video. Obviously, I don't think you're doing this in real time. I don't believe, is it?
Well, okay, when I say we applied it to video, so that's the famous word. So what did we do to video? So one way that I describe this work to psychologists is when they show people 2 sinusoids at a time, they're doing a very bottom-up approach to providing stimuli, right? Let's take this frequency and this frequency, and then let's take this frequency and this orientation. And from our perspective, bottom-up has too many combinations, right? We couldn't possibly do that. So this was sort of a stochastic top-down approach. Let me take a bunch of different images as masks and sort of average all the results and see if this gives me something meaningful. So what we applied to video was the same top-down approach. Instead of trying to create very, very detailed and narrowly described stimuli, we took 3 different video coders, which were selected for having vastly different techniques, so the artifacts were vastly different. 8 sequences with a huge range of content, ranging from very, very low motion to very high motion in sports. And then we coded the 8 sequences using the 3 coders, using 5 different combinations of bit rates and frame rates. So now we have all kinds of coding artifacts which are induced by various rates and frame rates on various types of content. And we showed total like 128 sequences to 30 observers and took real-time quality measurements. Does this look okay? And then essentially those quality measurements, what people saw, literally they had a slider, so we have a continuous trace for every video sequence. That's ground truth of whether people thought it was good or bad or wherever it was on the scale. And then could we develop, based on what we knew about visual system models and temporal modeling, could we develop a model that could accurately predict that gold standard? So from a standpoint of a top-down thing, that's effectively what we did with video.
Yes.
When you showed the map of the regions where you deemed acceptable to take on error,
Right.
and with the information that Glenn asked about relating to labeling of the blocks, how come we don't see the artifacts from your block labeling?
Because the distortions are, the blocks are so accurately labeled that remember that there are very few blocks where there is uniform stochastic wavelet coefficients. So you're only going to see the distortions essentially corresponding to the structure. Okay, so where you have large coefficients corresponding to textured areas or edges, that's where you're going to see the most quantization errors, and that's what shows up here. That's an excellent question. Okay, now also keep in mind, this is at threshold. Okay, if we turn the rate way down, at some point you would start to see that. Okay.
Any other questions? All right.
Thank you all for coming.
Well, it's up to you.
Okay.